Yes, so welcome to the afternoon. After the midday session, now we will have another keynote that will be heading into our last session of tracks. And then in the end, we will have our panel discussion, which I'm also looking very much forward to. The afternoon will be started with the keynote of Professor Dieter Fox. He's from the University of Washington and also NVIDIA. And we have a great collaboration over the last 1.5 years where we are looking at how can we teach robots more intelligent and autonomous skills. And Professor Dieter Fox will talk about how can we actually go towards object manipulation without like having the model of the object that we want to manipulate, right? So that is quite a challenging task. We were looking into just grasping and also packing objects that we don't know before. Grasping is much easier because you can look at the 3D form and then you can know a grasping point. But how would you place something that you don't know what form it has, right? You grasp something as a robot and then you don't know the form of what you grasped. So how would you place that? So that's quite challenging. I'm really looking forward to the talk. Dieter, please go ahead. You can share your slides. You're on the big screen, and yeah, enjoy the talk.
Okay, excellent. Thank you so much for inviting me over this very exciting opportunity. And also, yeah, I very much appreciate the collaboration that we're doing with the Festo team. And as you mentioned, there the focus has been so far mostly on actually doing manipulation of objects for which we do have models. And today I want to focus on work that we're doing in the research lab towards being able to manipulate objects in general, object manipulation tasks, even if we don't know the objects in advance. Can you see the slides now?
No. So you have to share your screen. I think it's not shared yet.
Oh, sorry. Okay, let me do that quickly.
Yes, now we see it. Great.
All right, perfect. Yeah, just very briefly as context. So as Manuel said, I'm half-time faculty at the University of Washington, doing very similar research also in robotics, and I'm leading the research robotics team at NVIDIA. And here our goal is really to do basic research such that we can enable kind of this next generation of robots that can operate in open-ended, unknown environments, working around people with dynamic scenes and also environments that are complex enough so that, for example, again, you don't know exactly what will happen in advance. Use cases for these are obviously many of them in manufacturing, logistics, but also healthcare sector. For example, having robots helping elderly people, people with disabilities lead an independent life in their homes, for example, is, I think, a very positive goal of this kind of work. Again, today I want to focus on how can we enable manipulation of unknown objects. And just to put this in context, here's some work that we've done more on the side of what you might call model-based manipulation. What you see here is on the left-hand side. I apologize already for the video quality on your side, but I hope you get the gist of what's going on, where the robot is tasked to put an object into one of the cabinets up there in the kitchen. On the right-hand side, you can see kind of an internal representation of what's going on for the robot. So the robot has a depth camera to observe the scene. And what you see is actually a colored, what we call point cloud of the scene. And the robot also has a 3D model of the kitchen cabinets. It has 3D models of the objects. And in these colored scenes here on the right, for example, you can see the different objects that the robot has detected. It can then match these 3D models that it has of these objects into the scene and use them for manipulation planning. So it can now use this internal model to plan, for example, where it needs to move the gripper in order to open the door. It has to grab the handle. It plans a certain trajectory to open the door. And then it can use the 3D model that it detects on the right side to determine how it can pick up this object. It can now do collision-free motion planning in order to move the object into the cabinet. Now, this already highlights some of the advantages of having models of the environment, because the robot can use them in order to do reasoning such as collision checking. It can reason about, can I even reach an object? What do I need to do to, for example, put an object into the cabinet? And all of this can be done in a fully automated way using techniques such for long-term, what's called task and motion planning in robot manipulation. Now, this also comes, of course, with some limitations. The first one is, well, it requires these models of the objects and models of the environment. And in many more open-ended tasks, we might not have access to these models. Another problem is also that because we tend to feed the system through these bottlenecks of estimating the poses of objects and reasoning about models of these objects, the execution of these tasks can actually become somewhat brittle if the pose estimation, for example, isn't highly accurate. So today I want to give you some examples and directions in which we are thinking of enabling manipulation without these kind of object models. And there's two kind of areas. The first one is model-free grasping and placing of unknown objects. Again, the traditional approach to what we call model-based grasping is the following, where we have a scene of that the robot observes, as you can see here on the left. We have a 3D model of an object that the robot, for example, might want to manipulate. And then the first task is we train, for example, a deep neural network that gives us the position of the object in the scene. In this case, this would be a 3D rotation and 3D translation. And we might also then, if we want to pick up the object, we might have the 3D model of the object, as you can see down here. We might have annotations for how the robot should pick up this water jug, for example. And we can now use the position of this model in the scene in order to say, to determine where the robot needs to move its gripper in order to pick up the object, which means we transform the grasp into the 3D scene, and that then gives us the grasp position for the robot. Again, if this pose estimate, this RT here, is inaccurate, then the transformed grasp will also be inaccurate and the robot might fail to pick up the object. As an alternative, what we'd like to look into is where we say we have an observation of the scene, and the robot might not even have a 3D model of the object, and we train a deep neural network that goes immediately from the scene to where the robot might pick up an object. This avoids this bottleneck of reasoning about the position and rotation of an object explicitly. So how can we do this? Let's look at one example task that we might want to execute on our robot. What you see here on the left is just an external view that is showing you what's going on in the scene. So there's our robot. It's standing in front of the table. And what you see on the right is the view of the scene as perceived by the robot. The robot has, you can see this here on the gripper, it has a depth camera. And with this depth camera, it can see the scene as you can see on the right. And now let's assume the user somehow indicates either through a mouse click, or also there could be, of course, detection models and things like that, but might indicate that the robot should retrieve this white coffee cup from the scene. And you can see that that's not a trivial task, because the robot needs to actually first figure out what is the boundary of that object, how can it grasp the object, and how can it actually reach this object in a collision-free way without pushing or colliding with other objects in the scene. And we're trying to do this without knowing anything a priori about this object. So the first thing we would like to do then is actually segment out the scene, which means segment the scene into the different objects that are there so that the robot can reason about them individually. In order to do this, we can train this, of course, in simulation. And here we're using, this is an earlier model, but this is kind of using Isaac simulation from NVIDIA, the replicator tool, where we can automatically generate many, many millions of examples of 3D scenes, and we can render them, as you can see here on the left, in color and in depth. And we can do this at different levels of quality, depending on what the task requires. And the advantage of doing this in simulation is that we also get for free, we get the labels of what are the individual objects in the scene, as you can see here on the right, indicated by the different colors. And we've done quite some work on training now deep networks that can take this data in order to segment scenes. Let me just give you one example of how this now works, where a network was trained to take as input, for example, these images that you can see here on the top row. And in this case, the network was trained to map each pixel in the image into a so-called feature space. And it was trained such that pixels that belong to the same objects have a similar representation in this feature space, and that representation should be different from objects, from other objects in the scene. So what you can see here in the second row is now a visualization of this feature space, the feature map. And you can see already that somehow the different objects are grouped pretty well according to similarity also then in color. And we can then perform clustering on these, let's say, features and colors, and we get a pretty nice segmentation of the scene. Okay, and this is purely trained in simulation, and it actually transfers very well to the real world. You can see here the boundaries and outlines of the objects are pretty nicely marking the different objects in the scene. So this solves our first problem, which means we have a scene and it's not just a bunch of pixels, but actually the robot can now reason about individual objects. The next thing is, if we have identified one of the objects that the robot should pick up, how can the robot determine how to grasp it? Here's one additional example also that this works actually pretty well, the segmentation even on scenes with transparent objects, where on the left you were able to see, when you go back here, the transparent objects on the right, you can see that they're pretty well segmented. Now, how can we train to grasp these objects? And here again, we're leveraging simulation. In this case, we're actually using full physics simulation. And the idea is as follows. Imagine you have an object like this red object that you can see here in the scene on the left. You have the 3D shape for this object. And we would like to figure out how could a robot pick up this object. So what we're doing here is the following. We're just randomly generating 3D or 6D gripper poses around the object. Like these are just possible ways for how the gripper might grasp the object. We then close the gripper around these randomly generated poses and shake the object in a 3D, in a physics simulator. In this case, it's Isaac Sim, in a physics simulator, in order to find out whether the object is in a stable position or not. So if the object in this simulation here flies away, that means that this was not a good grasp. So, and we can do this on a GPU all in parallel, and we can do this for many different objects. Here on the right, you now can see, for example, what we get out of this is, for a 3D object, we get many different ways of how the robot might pick up this object. Successful grasp positions for gripper. Visualized here is, for example, one. We can do this for a large data set, as you can see here on the right. We did this for the ShapeNet data set. There's more than almost 9,000 different object shapes. And what you can see here on the right is also these green kind of gripper poses around these objects that indicate poses that were tested as successful grasps for these different shapes. And here this gives you an idea for the scale of this data set. So now what we have is we have a large data set of shapes, and we have each shape annotated with successful grasp poses. We can now use this to generate training data, again, for a deep neural network in order to replicate these. And we can feed this now into a network that performs reasoning in order to go from a point cloud observation to a grasp for unknown objects. I just want to give you the gist of how this now works. So we can, in the simulation, again, we can generate for a 3D shape, we can generate the so-called point cloud, meaning we don't present to the deep network the perfect shape model of an object, but we present to the network a view that the robot would have of the object using a depth camera. So you can see here, if you look at this input here on the left, that there are gaps in the model, right? So because there are occlusions when the robot sees the object from a certain viewpoint. We can now use the deep neural network, and this is what's called a conditional variational order encoder. There are different ways for doing this. But in this case, we can train a deep neural network that takes as input this point cloud and generates different possible grasp poses for the object. And it does so by trying to replicate the training distribution that it gets from the data that I showed you on the previous slide. Okay, so we can then, once this network is trained, it kind of learned what a successful distribution of grasp looks like if you get as input a point cloud of an object. Now this grasp sampler is not perfect, so there might be some inaccuracies in this. So we can now train actually a second network that gets as input a specific grasp example, and it evaluates how likely it is that this will lead to a success. And again, we can test this through the physics simulation. So here on the right side, you can see, for example, that the top grasp is something that is likely to lead to a success because a robot would grasp the coffee mug at the handle, and the other two might actually not work out. And since it's a deep neural network, it is differentiable, which means we can actually refine the grasp poses in order to increase the probability of success. I encourage you to take a look at the papers for details for how this works. But with this pipeline now, we have a system that can take a point cloud of an individual object and generate suggestions for good ways for picking up the object. Here's now how this works in the real world. These are just some examples for the robot picking up these objects. Very importantly, the network was solidly trained in simulation, and we did not do any additional refinement in the real world. So we have a very good success rate for objects in the real world. And also importantly, since the network was trained on almost 9,000 objects, these specific objects were not part of the training data set. So the robot was able to pick them up without having ever seen those specific object models in the simulation. So now this shows only picking up an individual objects, but how can we go back to our original task of picking up objects in a more cluttered scene? And for this, we extended this approach in the following way, where now the input is this more cluttered scene of different objects on the table. The first thing we do is segment the scene using the segmentation network that I briefly showed you at the beginning of this talk. And let's assume that user identifies that object number 3 is the one the robot should pick up. We can now generate a point cloud kind of centered around this object number 3, which is the yellow mustard bottle. We can feed this through our grasp network that generates possible grasp for picking up the object. This was just trained on this very large data set. And finally, we can actually train another network that looks at the other objects in the scene and figures out which of these grasps are actually collision free, because some of them might actually collide with the other objects in the scene. And the advantage of doing this through another deep network is that the deep network can actually learn to reason about occlusions or collisions with objects that are partially occluded. So this turns out to be more robust than only checking for collisions with points that are observed by the robot, because the robot does not have perfect information about the scene because it only observes a partial point cloud. Now let me go back to our original task and show how we can put all these pieces together, where again, the task of the robot is, let's say the user indicates pick up this object. You could imagine you just click on an image and say, this is the one I would like you to retrieve. The first thing the robot does is segment the scene. This is now the target object. It generates the grasp for this object. And it also reasons about collisions. And what you can see here is colored the other objects in the scene. And the coloring indicates by how much they contribute to collisions with the gripper poses that we would like to achieve if the robot should pick up the white coffee cup. Which means in this case, the red object, which is the sugar box, is the one that is mostly contributing to the collisions, which means the robot cannot pick up the object right now. So what we do now is we say, well, in order to pick up the white object, the best thing the robot can do is pick up the red object in this scene in order to get it out of the way. So now we do the same process by saying the target object is actually the sugar box, which is labeled here in red. And the robot now identifies that for this object, there are grasps that are not in collision. And it can now go and actually pick up this object, grab it, move it out of the scene. And now it can go back to the original setting and say, okay, now can I pick up this coffee cup? It turns out now the coffee cup is actually reachable and it can generate automatically the right grasp and we can pick up the coffee cup as desired. So very importantly, none of this requires an explicit 3D model of any of the objects. This works without knowing what type of object it is or any of the explicit 3D models. We recently, this is an upcoming ICRA paper, also extended this to do, for example, now kind of grasp and placement reasoning in more complex scene, as you can see here. So here the collision checking is becoming more complex because the scenarios are more difficult to reach the different objects. And the robot can also reason about where it might be able to place an object without causing collisions. Again, none of this requires explicit 3D models. One final example of this is now here we can use the same kind of grasp network that we trained on these 9,000 simulated objects in order to enable the robot to retrieve objects from a person. So in this case, the robot actually segments out the objects and reasons about how it can grasp the object without pinching the human's fingers, for example. Again, I encourage you to take a look at the papers if you want to know more about the details. Okay, so this is the first example I wanted to give you, which again is about enabling the robot to reason about and grasp and place unknown objects. It is somewhat still, let's say, a traditional way of thinking about manipulation in the sense that we're still trying to segment the scene into different objects. For each object now, we're trying to figure out how we can grasp this object, and then we're reasoning about explicitly how we can place the object in the scene. Now, this works well if the manipulation task is about grasping objects, but there are other tasks that are not so easily specified in this what we call, let's say, object-centric way. One other thing to recall here is also that we were able to train all these systems purely in simulation, and they transfer actually very well to the real world. So now I want to give you an example of, instead of going this what we call object-centric way for manipulation, there's another kind of representation we've been looking at is what I might call action-centric manipulation, and also going towards using language in order to inform the robot about what it should do. So let's look at this, the following task here that we can see here on the right. Let's assume we would like the robot to pick up the tomatoes that you can see here on the left and put it in the top bin. which is on the right side, one of these two bins there. The traditional approach, even for unknown objects that I showed you on the previous slides, would try to segment the scene. You then would try to detect, oh, which are the tomatoes in the scene. Then it would generate grasp poses for the tomatoes, like how the robot could pick up the tomatoes. Then you would have to detect the bins on the right side. And then you would have to kind of identify which of the two bins is the top bin versus the bottom bin. And then you would do planning in order to move the tomatoes into that bin. So this is the task we want the robot to execute. And again, this already turns out to be not such a trivial task to specify, especially in this case, for example, how to pick up these tomatoes and to identify which of the bin to place it in. So in this line of work, this is work done in collaboration with my student, Moit Schroeder at the University of Washington. It's called Perceiver Actor, which we just presented in December at a conference on robot learning. We're trying to train the robot to perform such tasks in a less object-centric way, where we're using imitation learning, which means the human demonstrates the tasks maybe a few times, and just from these demonstrations, we want the robot to be able to execute them. The important piece is that the demonstrations do not include any information about what the tomatoes are or what the bins are. They only show where the robot should move in order to execute this task. The input to our network is a 3D representation of the scene. You can see this here, hopefully, on the left side, which is what we call a 3D voxelization. So how we represent this is the scene is like by a 3D grid, and each cell in this 3D grid has the size of 1 centimeter cubed. So it's a pretty fine-grained representation. And in each of these voxels, we store whether this is an occupied voxel, whether there's a surface or an object at this voxel, and also the color of the voxels. You can see this again visualized on the left side. So this is the input to the network that we want to train. And the output for this scene is where the gripper should move in order to execute the task, which in this case would be put the tomatoes in the top bin. You can see here visualized on the left side, hopefully, this bluish shape that is the position where we want the gripper to go in order to execute that task. This is a multi-step task because the robot first has to grip the tomatoes, then it has to move above the bin, and then it has to open the gripper. So for each step in this task, the network has to generate a target position of the gripper. Okay, and again, the important aspect here is that we never specify this through labeling objects in the scene or something like that. We only specify it through desired gripper poses the robot should achieve. Now, I just want to give you very briefly an idea for kind of the structure of this deep neural network. And we're using an architecture here. It is called a transformer architecture. And I'm sure many of you have heard about these amazing successes that we've seen, for example, in recent what's called large language models. Might have heard of things like GPT-3, and more recently, of course, it's gone all over the world through the press is ChatGPT from OpenAI. And all these models use an architecture underneath, which is called a transformer architecture. I'm not going into the details here, but the key trick in this case is that we're using a very similar architecture, but rather than reasoning about words, which is what these chat agents are doing, here we're using a similar architecture in order to reason about the 3D voxels in a manipulation scene. Okay, So the input to the system again is a 3D voxelization of the environment. It's overall, the size of the scene is 1 meter by 1 meter by 1 meter, which is 100 cubed voxels, a million voxels. And then we downscale them to actually through a 3D convolution layer into only 20 by 20 voxels, which are now becoming inputs to our network. So you can see here in the scene, we have this what's called a voxel encoder. And we also have a language encoder, which is using the words that are describing the task. For example, open the middle drawer. And it uses an encoding that comes from these pre-trained large language models. And it just takes all these voxel encodings and the word encodings and feeds them through this transformer architecture. And again, this is very similar in spirit and the internal reasoning that is going on in these very large language models. And the output of the network is, you can see this here, hopefully a little bit on the right side. The output of the network is, well, if this is the current scene and this is the task, the output is where should the gripper go next in order to make progress on this task? Okay, so it's a multi-step task. So again, what is the next gripper pose? 3D translation and 3D rotation, whether 3D rotation is a discretized output for the network, and also whether the gripper should be open or closed, because sometimes it has to grasp an object. The trick is that we are leveraging, again, these modern deep network architectures that have been so successful for language models and also for computer vision models recently. Now, here's one example for how this works for our kind of example task here. Put the tomatoes in the top bin. For training data, we just demonstrate the task to the robot a few times, where we're generating the movement of the robot either through remote control or by manually moving the gripper to the target positions. And we're generating snapshots of the scenes for where we want the gripper to go. For example, first we want the gripper to go above the tomatoes, then it should go slightly down in order to grasp then it needs to move in the next snapshot. Let's say it needs to move above the bin. What you will see here on the right side is the internal representation of the network, which are these voxels, and the red dot that you can see here indicates the next gripper target that the robot should achieve in order to perform the task. So let me now start the video. I hope it's not too choppy. Here's the gripper, the target gripper the robot should achieve. Now, this output is used by the robot on the left side in order to move there. Once the robot moved there, we take the next snapshot. You can see now on the right side, the network generates a desired gripper pose that is further down towards the tomatoes. And it should close the gripper. Now on the right side, you see we generate a new gripper pose that is retrieving the gripper to move the tomatoes up. And the next target pose is above the bin. Again, very importantly, nowhere in the training data did we identify the bin. So between training and testing, the positions of objects can move, but the task itself should be the same as it was during training. Now, what's interesting here is that this can be trained from actually only few demonstrations. What I'll show you now here are examples for the robot executing these tasks only from 53 demonstrations, which can actually be performed pretty quickly. So the first one, the robot was trained to press the top of this hand sanitizer model, and it just indicates that the system is actually able to pretty robustly, even at different locations, or here, put one lime in the bottom bin and then put the tomatoes in the top bin. Can open the drawer, it can pick up an object and move it in there. Very importantly, All of this was just generated from 53 demonstrations, and the demonstrations were annotated with the text that you can see here, for example, at the bottom. And it isn't, of course, perfect. It sometimes might fail to pick up an object. And these are tasks that are not so easy to specify through object detection and things like that. Let me give you some more examples for tasks was the prior work that reasoned more about top-down grasping, but it's kind of the same idea here. And again, it's not so easy to specify such a task, for example, through an object detection, because what it means to move the rook one block to the left, there is no detector for the block left, because it's a chess defined by the chessboard shape and the position. So the network needs to learn this just from the training demonstrations. Or here's another example: sweep the beans into the blue zone. And this is hard to specify because if you would like to have a detector for every single bean, it's very tricky to do this kind of task. Let me give you one final example here: pick up cherries. And here the robot needs to actually learn to pick up the cherries at the stem, because we don't want to squeeze them. And again, this can be done from very few demonstrations. In this case, it works pretty well. All right. So these were examples for manipulation tasks that we can train from very few demonstrations. Also, that can take language context into account. Have in mind that these executions that I showed you were all performed by a single neural network. So the single neural network learned not only to perform one specific task, but it learned to use the language specification for the task in order to execute this. A big caveat is that I'm not indicating here that the robot learned to really understand language. What it learned to understand is the specific commands that we gave in the training data. This is important. Moving forward with this line of work, what we want to do is now, rather than training such a large network, these transformer networks that have been so successful for training language systems, we want to train them, rather than using, let's say, only 100 demonstrations. What we want to move on to is now, what happens if we have 1,000,000 demonstrations that we can perform all in simulation? So we want to train a robot to perform thousands and millions of tasks in simulated, generated environments, and hopefully that such a network can learn very general manipulation capabilities. So this is an ongoing project that we're currently pursuing at the lab. So in the remaining time, I would like to briefly show you some examples for how we can use also simulation for training, where I give you some other examples for simulation use. The one is that is more relevant, of course, for the industrial kind of applications that many of you might have in mind, is a high precision manipulation task, where the previous line of work I showed you at this point wouldn't scale really to the precision that is required for these kind of tasks. What you see here on the left is a task board that I can imagine many of you have seen. This developed by NIST, where the idea is insertion tasks, like putting a peg into a hole, or inserting plugs, sockets into these sockets, or screwing a nut onto a bolt. There's been a lot of work also on using reinforcement learning in these tasks. However, so far all of this has been done in the real world. And the reason why these tasks have only been performed in the real world and not in simulation is because simulation is actually very difficult for these tasks. I must admit, I was not aware of that. It turns out that simulating, even like threading a nut onto a bolt, is a very difficult task. As you can see here on the left, this is from work from 2018. It's very difficult to get this to be stable, which means in order to perform the simulation of this, you need to reason about all the tight contact surfaces between the nut and the bolt in order to compute the surface contacts and the forces acting upon the different objects. There's a paper from 2020, and this was kind of state of the art at the time of our work, where they showed that they can actually perform this task. You can see this here now on the right. So it's a stable motion of this threading operation. The two caveats here is, first of all, this was kind of more like a toy scale nut and bolt, not industrial scale, very tight margin operation. And the simulation took 350 times longer than real time, which means 1 second real time threading was 350 seconds in simulation. So we went and worked with NVIDIA, the internal physics simulation team, in order to come up with a representation that was very well suited for GPU processing. I don't have time to go into details, but we were then able to perform this kind of simulation tasks here on physically accurate nut and bolt settings. I hope you can see this, where we can now simulate 1,024 nut and bolt operations in parallel on a single GPU. So rather than 350 times slower than real time, we are now at real time, but with 1,000 of them in parallel. So what this enables us to do is, of course, we can now go in simulation, which was beforehand not possible. We can now go into simulation and train robots on these very tight margin operations. You can see here on the right, it's just showing kind of an execution of a trained policy. And we also developed different kind of test environments for this, like different kind of insertion tasks. And in ongoing work, this is the first ones to see this, we were now able to actually, let me turn the audio off here. We are now able to execute tasks that we trained in simulation on a real robot. So to the best of my knowledge, this is the first time that this has been possible, which means these very tight margin industrial insertion tasks that were purely trained in simulation, and then without any adaptation, we can execute them in the real world. This work is currently under review at a conference. Okay, so I'm very excited about this. And we're currently extending this to also incorporate touch feedback so that we can actually perform these tasks at even higher precision and more with higher tolerance for errors. Here's the touch sensing example. I'm not gonna go into details again. I'm starting to get towards the end of this talk. Here's kind of you can see an example of what the sensor measurements look on a real touch sensor. This is a gel site, and we're currently developing a simulation version of that so that we can train using touch feedback inside our trained policies in simulation and then transfer that to the real world. We're also looking at, of course, simulating the deformable objects. Here on the left side, you can see simulating how a tube deforms. On the right side, this is actually tofu on the upper part, picking up tofu. And we have some work that you can take a look at the papers for more details. Reasoning about granular media. This is, of course, very important. Pharmaceutical, food industry. And the work here really also aims at how can we learn the simulation parameters so that the simulator behaves very, very closely to the real world. So how can we adjust the simulator to real world data as well? And finally, how to do all of these simulations very, very rapidly in order to train complex manipulation tasks. Here is some work that we will present at this year's ICRA conference, where you might have seen this was work that OpenAI did a while ago. And we can now do this on a GPU orders of magnitude faster than what they were able to achieve. And this is purely trained in simulation and then successful execution on the real robot. Let's wait for the last ping here. So with this, I'm gonna come to my conclusion. So first I want to say, of course, in many industrial settings, we do have object models. And I believe that clearly we should take advantage of these objects through, for example, object pose detection and reasoning, explicit reasoning about this whenever we can. At the same time, of course, there are limitations to that approach, and the reliance on explicit object models might actually make the system sometimes more brittle. In this work that I showed you here, the idea is that we try to train models that go from raw observations like point clouds or colored images and things like that to map directly to properties that are relevant to manipulation tasks. For example, we map directly to segmentations of the scene, to grasp poses of the scene, or also to kind of what are the spatial relations between objects. That can lead actually to robust execution even for unknown objects, because we can train it on very large scale simulation. The action-centric representation, I showed you the examples, is the idea here is that rather than reasoning about objects explicitly, we are actually reasoning much more about what the robot should actually perform, which means where should it move the gripper in order to achieve a task. And I showed you that this can be trained highly efficiently using demonstrations. I believe physics-based and photorealistic simulation is, of course, now really within reach, especially if you look at the recent advances we achieved with the Isaac simulation at NVIDIA. The advantage of these simulators, of course, that we can perform safe training. We can do training at scale, which means we are now open to doing reinforcement learning and any kinds of training system in simulation. The other advantage, of course, of using simulation is also for training, benchmarking for the research community, so that, for example, you can evaluate how well your certain algorithm operates and compare it to other teams. And I think where we want to move is really toward what we call these general manipulation models. Again, you have heard of these very general, broadly capable language models that people can use that are trained on just incredibly large amounts of data. And I believe that in robotics, if we now kind of start to leverage similar kind of learning models as these transformers that I showed you, I think we can also go towards training systems that are capable in the real world when they are trained at scale in simulation. And with that, I'll thank you for your attention.